Okay, welcome everyone. So this is another exciting talk by Itamar. So he'll be talking about processing large JSON files without running out of memory. And he's a consultant and writes about Python performance at pythonspeed.com. Stay put and listen to this amazing talk. Please check him as he starts the talk.
Hi. Hi, my name is Itamar. Talking about processing large JSON files without running out of memory. And I should add that JSON is a thing that lots of people use, and so I'm going to tell you how to process it without running out of memory. But the techniques I'm talking about are much more general. These are in some ways examples of how you apply these techniques for one kind of data, but anytime you are processing data that's larger than memory, you will end up often using very similar techniques. So in other situations as well, you can use these techniques. Before I talk about the software you can use, I want to talk about software you shouldn't write. I grew up in Israel, so here's an example from there. So in about 2 years, Israel killed about 69,000 Palestinians in Gaza, which 20,000 were children, and this relied heavily on software. In particular, in previous military conflicts, they ran out of bombing targets pretty quickly. And they had this pressure to just keep bombing at a much higher speed. And so they turned to software and they used some AI models. And some of these AI models had known problems. And the AI models are basically a result of just this pressure to do things quickly. And so you shouldn't be writing software like that. And this is an extreme example, but it is an example of a broader problem, which is anything that software can do, you can do, right? You can do math in your head. You can do math on a piece of paper. So like, the computer is just amplifying something. And often that's very, very useful. Like, the computer can do arithmetic like billions of times faster than you can. But if your software is causing damage, if it's hurting people, if it's hurting the environment, then by amplifying it, by making it go faster, making it more efficient, writing it at all, you are causing much more damage than if a person had to do this or if you had slower software. So before you get to the point of how do I make my software more efficient, you should always be asking, should this software exist at all? Should you be working on it? And if maybe you shouldn't, in that case, you should probably be figuring out something else to work on rather than thinking about how to make it faster. So for the rest of the talk, I will be assuming that you've already made this decision and talk about the actual main topic. So imagine you have a JSON file. It is a list of dictionaries with some data, and here's some Python code you could use to load it. So you import JSON, you open the file, you call JSON.load, and then you iterate over all the entries. The file is 50 megabytes, but if you measure the peak memory of this process, it is 230 megabytes. So you're using about 4.5 times as much memory as the file was on disk. And in some sense, this is fine, right? Because your computer has lots of 16 gigabytes of memory, 32 gigabytes of memory. So like 200 megabytes, who cares? You load the file, you process it, you're fine. But sometimes you have a larger file. Let's say you have a 10 gigabyte file. So if we have a 4x multiplier on the memory usage versus file on disk, now when you're loading a JSON file that's 10 gigabyte of disk, you're using 40 gigabytes of memory. If you're on a computer that has, say, 16 gigabytes of RAM, like the physical hardware used to store stuff in memory, you have a problem. You're trying to shove 40 gigabytes of data into just 16 gigabytes of RAM. And so there's two things that can happen here. One thing is the operating system will say, oh, this doesn't fit. And so I'm going to push some of it back down to disk. And so now you're trying to process, the amount of data you have is 3 times as much as what fits in RAM, and so it's continuously moving data between disk and RAM. Disk is much slower than RAM, and so your program is just going to get slower. Sometimes much, much slower, depending how much reading and writing from disk it has to do, how much swapping. The other thing that can happen is your operating system may say, you just loaded a lot of memory. This is ridiculous. You do not have the hardware for this. I'm just going to kill you. And so your process just loads data, and then just gets killed. You just never finishes. So you have this range of possibilities between a little bit of slowdown, large slowdown, or just dying, in which case your program never finishes. This actually is a problem. And one thing to notice here is the main problem is peak memory, not average. So if you're thinking about whether your software is fast or slow, if your program is slow in one part and fast in another, that's fine. It all gets at, like, if you optimize the part that's slow, then it'll optimize the whole program. Like it all adds up. Like in memory usage, what matters is the peak. Like if your average memory is 10 gigabytes of RAM, that's great, but all it takes is one moment when you hit 40 gigabytes for the operating system to say, that's way too much and to clear your process. So it doesn't matter what your average memory usage is. For optimizing the memory usage of your program, you have to care about the peak. This is specifically for data processing applications. If you're doing like a web server, there tend to be different issues like memory leaks. So I'm talking more about kind of program where you load some data, process it, and then write a result out. And these programs have to be very intensive, and then the peak is usually what gets you. So you want to measure peak memory. There's a bunch of different ways. My favorite are memory profilers. I wrote 2 of these, fill inside graph. Memory is the most fill is the easiest to use. Memory is the most cross-platform. It runs on Windows, Mac OS, and Linux. But there's like, for this presentation, I just use the command line tool on Linux, user bin time. In verbose mode, it will tell you the maximum resident memory. You can access that from the Python standard library. There's a thing called tracemalloc in Python that tells you allocations of Python objects. You need to use the right measurement for the different purposes, and that's not the main point of this talk. But the important thing is, like, you do need to measure this. If you don't measure it, you won't know what's happening. I'm mostly using the first method here. I wrote little programs and then just ran them. And I'm going to cover, in the rest of this talk, 4 solutions for solving high memory. Buying RAM, using a more efficient in-memory presentation, only loading the data you actually care about instead of all of it, and streaming, also known as chunking or batching or what have you. And these are all generic, as I said, generic solutions. So even if you're not using JSON at all, you'll often find yourself applying some subset of these solutions in order to process more data that can fit in RAM. So the first solution is you just spend some money. RAM is the physical component in your computer where data is stored. If data doesn't fit in RAM, it gets written to disk temporarily, known as swapping on Linux and similar operating systems. And the problem is that disk is much slower than RAM. That's why you have both. And so you don't want to be reading or writing data from disk if you can help it. And so more RAM means less need for swapping, means your program will run faster, and you're less likely to hit the operating system limits will just kill your process. You can buy more, for some computers, you can just buy more RAM. There might be a limit, or if it's a Mac, you physically cannot upgrade it because it's just built in. You can buy a new computer, buy a used one. If you get using stuff in the cloud, then you have access to very large amounts of memory. And you pay by the minute, and so you can say, well, I'm going to run this program for 1 hour. It's going to use 16 terabytes of RAM. I'm only ever going to run it once. I've debugged it already, so I'm just going to do this and pay for 1 hour, and I'm done. Right? And that may be a fine solution. You don't have to write any new software. You just have to spend some money. But this doesn't always work. So one problem you can have is you're going to be scaling up. You're going to be running this program over and over and over, a large amount of data over time. And so now the extra cost of paying for 4 times as much RAM as you actually need add up because you're doing it at scale. Or you have to buy lots more computers if you're building a computer lab. This is a problem. RAM is also much more expensive now than it used to be. Over the past year, prices have gone up 100 to 200% because there's so much demand for RAM for AI chips that like just RAM for your computer is just costing more. I don't know if that's percolated into cloud computing, but like if you're buying hardware, it's just going to be more expensive than it used to be. Buying RAM doesn't help if you don't control the runtime environment. If you're distributing an application, it's going to be used perhaps by many other organizations or people on a variety of computers. You don't know in advance what they'll be. You can tell them you need to buy lots of RAM, but they may or may not do that, and they might be annoyed. They're asking them to spend more money, so that might not work. Or you don't know in advance how much data you're processing. right? If you're just going to load the whole file into RAM, that's just how you do it. That doesn't work if your users or you are going to be loading a large variety of files you can't predict the size of in advance. Like maybe it's fine with a 1 gigabyte file, but not fine with a 20 gigabyte file. If you don't know what the size of the data is in advance, then just telling people to spend more money isn't going to work. And at some point, you'll hit the point where you cannot buy enough RAM memory. And so when buying more RAM doesn't work, the next thing we have to look at is writing software. And so those 3 techniques we're going to cover. And the first is a more efficient in-memory representation. And one thing to think about as a start is why does it take so much more memory to have the JSON file objects in memory compared to on disk? And there's 2 reasons. One is some libraries just do something by mistake that is inefficient, and these problems are often easy to solve. So maybe it loads all the data and then makes a copy when it processes it in one way, and then makes another copy, and it forgets to clean up the intermediate values when it's constructing the final one. And so you end up with too much memory, and then if someone went and submitted a pull request and fixed the code, then it would use less memory. And that's some of it. But there are other more fundamental problems that make this harder, which is by default, when you're loading JSON, you're creating Python objects. And Python objects are not very memory efficient. So consider the number 6,752. If you write this to JSON, that is between 4 and 6 bytes on disk. You have 4 digits, then maybe you have a comma, or maybe you have a comma and a space. But it's just going to be about 4 to 6 bytes on disk. If you load that into a compiled programming language like C or Rust, if you do like a 64-bit integer, then that will be 8 bytes. Still not that bad. You can load this into a smaller integer, like a 32-bit integer, then it will only be 4 bytes. But if you load that into Python, a Python integer is between 24 and 28 bytes. And so if you have a whole bunch of integers and you load them from disk into Python, you're just using a lot more memory just because Python integers just have higher overhead. When you do 6,752 as a Python object, it just uses a bunch of memory. A Python dictionary is 64 bytes of memory. I think a list is like 56 bytes of memory, something like that. And so when you're loading a JSON file, you're creating lots of lists and lots of dictionaries and lots of integers and lots of strings. And there's just a lot of overhead because of the way the Python interpreter works. In other programming languages, it's less of an issue, but anything that's interpreted is likely to have this issue. So that suggests maybe a different representation. And so one library you can use in Python is a library called awkward. It's originally from physics. It lets you do different length arrays. And it uses the underlying memory format is arrow. And arrow can be is what polars uses. So you can load into polars. Pandas in newer versions has started transitioning to arrow, so you can just transition into pandas without any memory copying. And so you just import this library, load a JSON file, and then if you measure the peak memory, it's 140 megabytes. So 2.8 is the size of the file. And previously we were at 4.6, so this is an improvement. The thing is, what you get at the end is not what you're used to. Like if you load a JSON file in Python, you have lists of dictionaries and you just process them however. And if you're loading them like this, you're getting a completely different kind of object. You can transfer it to polars or pandas and work with those. You can use the awkward array API. But either way, you're just transitioned to a completely different API in order to get a more efficient memory representation. I did try polars and pandas themselves, and they use way more memory. Again, this is the kind of higher memory usage which I suspect is easily fixable, but they haven't. So it's not, because they're all using arrow in the end under the hood. And so you can load a thing in awkward, pass it off to polars and use it. So this is not inherently high memory usage, it's just their implementations are not as efficient as they could be. Another option, besides a more efficient in-memory representation, is only loading the data you actually care about. So the data I've been testing with is a list of objects, or JSON objects, or dictionaries. It looks like this. It has an ID, a first name, a last name, description, and a timestamp when it was created. And just a list of these. And sometimes when you're processing this, maybe you're only looking at the ID and when it was created. Maybe you're doing some sort of visualization of time series of when things were created. You don't care about the other fields. And until now, we've just been loading the whole JSON file and then just throwing away half the data because we don't care about it. It's still using up memory. So what we'd like to do is only load the fields of this dictionary that we actually care about. And then we'll use less memory. And our program will work just as well because we didn't care about the rest of the data anyway. And so in Python, one library you can use to do this is called MessageSpec. And the way MessageSpec works is you can create a schema. You say, I have these records, and they have these fields. They have IDs, and they have created at as a float. And I only want you to load things that match this particular schema. First, you define the schema. And then using the, so you have to load unfortunately, you have to load the whole JSON file into memory, because there's limitations in the MessageSpec API, which is kind of annoying. And then you use a decode method, and you say, I'm loading a thing which is a list of records. So this is just documentation with Python's type annotations. It doesn't have any semantic meaning. It's just documentation of what you're getting back. This is the important part where you're saying, I'm loading a JSON string, and it's going to be a list of records. And then MessageSpec will only load the things you care about, and it won't bother when it sees fields you didn't ask for. It will just throw them out, drop them on the floor. So by the time you get the data, you're getting a list of these record objects, but they'll only have the fields you cared about. And the peak memory is 110 megabytes, and half of it is just this line, where you're just loading everything, the whole file into memory. It's kind of annoying. And so if that ever was fixed, you could probably do even better, and maybe only do like 70 megabytes of memory. So this is a significant improvement because you're just not loading data we didn't need. Another library which is much more popular than MessageSpec is Pedantic, which in theory has the same functionality. In practice, it also uses lots of memory. Again, this should be fixable, but out of the box, it is not as efficient as it could be. And then the final software solution is streaming or batching or chunking or incremental processing, which are all names for the same basic idea. So in all the examples I've shown so far, I have loaded the whole JSON file. Maybe only some parts of like maybe some fields got dropped, but I'm loading the whole thing. But instead of that, we can load the data in chunks. We can load a chunk of data, which is, let's say, only 10 megabytes. We can process it, and then we can drop those 10 megabytes on the floor because we finished processing it, and then move on to the next chunk. And so if we do that, the peak memory at any given time will only be around 10 megabytes. And we can actually process files that are 100 megabytes or a gigabyte or 10 gigabytes or whatever, and it'll only use the same amount of memory because we only ever have a 10 megabyte chunk of data in memory at a time. And this has some constraints. You need to be able, your JSON file has to be in a structure where this kind of makes sense. This is I've been demonstrating a list of dictionaries, which is pretty common, and then there's a very clear unit of how much to load. You can just load a bunch of dictionaries from the list. But some JSON files, if they're like an arbitrary set of nested dictionaries at arbitrary depth, it's a graph of some sort, trying to represent a tree or something like that, it may be that you cannot, there's no real meaningful way to load like a chunk or a consistent chunk of data. And the other limitation is this assumes you can actually process your data one chunk at a time. If you simultaneously need to use the first record and the millionth record to process the data, you have to load a whole bunch of data in order to do that. Maybe you can only load those two, but there is, if you need random access to your data, if you need to arbitrarily access different parts of the data, it is much harder to process things in chunks or often impossible. And in Python, the library to do this is iJSON. And you open the file, and then you use this little, you say, I have an open file, and I want a thing which iterates over records in it, and it has a little query language. And this the string item means every item in this list. So I have a list, and I just want you to give me an iterator of everything in the list. And then I have a record object, which is a dictionary, and I can just access the fields. And this basically uses like a fixed amount of memory, which doesn't matter. It doesn't matter how big the file is. This is going to always use the same amount of memory because we're not loading the whole file to the disk. It's just loading a little bit of data, parsing it, and then handing it to you. And you might be thinking, okay, but this is very similar to the original code. How is this different? So this is the original code. And here, we loaded all the data into a list. It's a list of dictionaries. And then we iterated over it. And so our interaction pattern is different, but the thing we loaded is different. In our original code, we loaded a list. In a list, you can access in any random order you want. You can load the first entry, you can load the millionth entry, you can load the 7,000th entry. You can access all these simultaneously because it's all in memory. With iJSON, we cannot do that. The only thing we can do is iterate. We can just say, give me the next one, and the next one, and the next one in order. And quite often, that is your interaction pattern. If you're only ever going to look at one item at a time, then you don't need to load a whole list. You don't need the random access. You can just load it incrementally and just use much less memory by constraining your ability to access the data to only in order that you got. And just to emphasize how this is different than the previous strategy we saw. In the previous strategy we saw, we did load the whole document all at once, but we only loaded some of the fields for every record. We said we don't care about the first name and the last name description. We still had the ability to do random access. With this strategy, we're loading records one by one. We can't randomly access the records from in an arbitrary order. We are loading a full record. But you can combine both techniques. It's once you're doing streaming, like loading only part of the data becomes less helpful. But sometimes you're loading into structured data with pedantic because that's just how you want to work on the data. But once you're doing streaming, the memory improvements from the subsetting technique aren't as useful, but you can do both because they're doing different things. And some final thoughts. First, JSON is just not a very good data format. And this is partly because, as you saw, like you end up using a lot more memory than you'd like. It's not designed for streaming, so doing incremental parsing is not always possible. It has a limited set of data types, which can get frustrating in some cases, like how do you represent a timestamp? It's not the fastest format to read, so there are some alternatives. One of them is Parquet, which gives you columnar data, like the kind of thing you'd load into pandas or polars. That has compression on disk, I believe, and it has a much richer set of data types, and the data types are extensible, so you can teach it about new data types. And so Parquet is great. Another option, which I'm going to show here, is New Line Delimited JSON. There's like 3 or 4 variants of this. They all have slightly different names, like JSON lines, and there's an RFC, and LDJSON, NDJSON. They all work basically the same. The idea is, the file I was loading is a list with a bunch of dictionaries in it, or JSON objects. So this is one JSON document. You have to load it all in one go. And then there's a list, and it has a bunch of dictionaries. But if we're only processing one dictionary at a time, we can say, how about we present this as a whole bunch of separate JSON documents? And in the text file, we're just going to separate them with a new line. So we make sure the JSON fits in one line, which you can do. You can do string coding to make sure it only fits in one line. And then we have multiple JSON dictionaries on separate lines. And you have to load each one of them separately. So you can open the file, and then we iterate over each line, which Python lets you do easily. And then you do JSON.loads of the line. So notice that we're doing the JSON.loads for every line in the file. So we're loading lots and lots and lots of separate JSON objects. And if we do this, the memory usage is going to be at whatever the Python is buffering the data to give you a line iterator, and whatever data you need to load one line. So your memory usage will be pretty much fixed. And you're just using a normal JSON library. You don't have to do anything special. And in order to do that, though, you did have to change to a different file format. Similar one This is not a JSON document. This is a series of JSON documents in one file. Another thing to take away is that measuring your memory usage is really important. We saw here a bunch of different libraries that were using way more memory than others, even though they were doing essentially the same thing. And this is for the versions I tested. In the future, that may change. Measuring memory is not done as frequently as measuring speed, both because it's more difficult and because it is often less pressing. Too high memory usage is much harder to notice because it's sort of a catastrophic failover. If your code is slow, it's like an incremental, like, oh, this is taking longer and longer and longer the more data I load. With memory, it's like, this is fine, this is fine, this is fine, now your program's dead. Because you use slightly too much data. And so there's a cliff rather than like things slowly getting worse. And so it's less noticeable and people are less likely to measure it and it's harder to measure. And so if you are processing a lot of data, I do encourage you to measure your memory usage because you can often say, like, if you're operating at scale, you can like save a lot of money in hardware by optimizing memory usage a little bit. So to recap, the 4 strategies: buy more RAM, use a more efficient in-memory representation, only load the data, a subset of the data that you actually need, and this is on a per record level, so like specific key attributes or fields or columns. And streaming, where you're loading the data one chunk at a time. And again, these are generic strategies. You can use them for other forms of data. The examples here are given are for JSON, but you can use these techniques elsewhere as well. So that's my talk. Thank you. Some of this is based on articles I've written that you can find on my website. That's a link to the slides. I do some consulting. I'm working on a book on performance, like speeding up your code. And I am happy to answer any questions you have.
I have a question. I mean, you put like different memory usage from different like sort of objects. Have you tried to use, like, have you measured like just Python classes, like data classes that use slots because they are more efficient than just dicts?
Yeah, so you can use slots on Python classes, and that will reduce memory usage somewhat.
But only number, like,
but
compared to like dicts?
You need something that can load into those. And like JSON library in Python, as far as I know, and maybe they've added a feature and I haven't noticed it, but like I think it just gives you dictionaries.
Right, but if you're sort of reading like line by line, right? If you don't keep them as dicts, but you just make classes. I mean, you can do it with Pydantic, like out of the box, but then Pydantic brings a lot of.
I don't know what Pydantic, like Pydantic ought to be using less memory.
Right. But I mean, if you have like data classes, you get rid of Pydantic overhead. But
part of, if you go and like read the documentation for message spec, like these record objects, the struct subclass, like the author has done a bunch of optimization. Make it use not as much memory as regular Python classes. Like you put a bunch of effort into memory usage.
Okay.
And data classes in Python with slots do use less memory, so you can reduce the memory, but you're still somewhat stuck with like a Python integer is going to be like just way more data. And if you switch to something like pandas or polars series, then the representation is using what a compiled language would use. So like a 32-bit integer is 4 bytes. And so you can say each integer in my pandas or polars series is 4 bytes versus a Python integer, which is going to be whatever it is.
Actually, which version of Python did you use to get you measures? There was.
I think this was 3.12, maybe 3.13.
There've been lots of improvements. Like,
yeah, there are improvements. There are fundamental difficulties in making it lower. Like a Python integer has to record that it is an integer in the first place.
Right.
It needs to record that whether or not it is bigger than 64 bits because it can be arbitrarily large. So there's overhead in Python that can be reduced and will help, but like has like fundamental limits.
What's the movement right now to use this type annotations to actually improve the memory? Like I don't know, it actually made it into release.
That is a thing that could, like, yes, part of this could be solved on the level of the Python interpreter. But that is a hard problem, and So like if they do a JIT, then that might help, but there's a limit to what it can do, and I suspect these techniques will continue to be necessary even with improvements in Python.
So you mentioned message spec. You mentioned a couple other libraries, and like polars and pydantic are like the things that everybody sort of like, or at least I have heard of before. How do you like? Is there a set of libraries that you tend to go to for things like this, or how do you like keep track of, I guess, the world of optimization in this kind of thing? Like, how do you find these?
I like polars a lot, and if I'm doing data processing, I would stick to it by default. Polars has a streaming mode you can turn on when it'll process chunks, data chunk by chunk, insofar as it can for you. The last time I checked, I don't think it supported for JSON documents. It did support it for like line by line JSON, but like if you just I have a 10 gigabyte single JSON document, I don't know that you can do lazy operations in polars, which is a prerequisite for the streaming mode. Because it's in the general like iJSON has that whole query language because it has to like, it can only support some situations. Like as a generic thing, it can't. So you could imagine contributing to polars as something like iJSON, where you have a little query language and you tell it the format, and you say this is a list of dictionaries, and then it would be able to use its streaming and lazy, like its lazy mode and streaming, and then polars would just do it for you. But last time I checked, it didn't do it for JSON documents. So if you're using like Parquet, then you can use polars with streaming mode and lazy mode and streaming mode, and then it'll do all the chunking for you, and it's great. So that would by default too.
I guess my question was more like, how do you like find the libraries or like, you know, keep track of this world of
basically have to measure.
Yeah.
Like I have contributed on behalf of a client some memory measurement tests to polars because I found a bug where they would do the, like, you want to load only some columns on Parquet, and it was like first loading the whole thing and then dropping to the columns you wanted, just as a bug. Someone introduced a regression, and so it's using way more memory than it should have. And I added some tests, and they had to roll them back because it would cause some issues running tests sometimes, and so hopefully they haven't introduced new bugs, but it's just harder to measure memory, and so it's basically, I think, a thing you have to do on your own. You're like, I'm processing a lot of data. I expect memory usage to be an issue. I'm going to measure it, and then with a profiler, you can say, oh, this is the library that's causing problems, or that's the library that's causing problems. You can like try to isolate it some more. Or sometimes you just forgot to delete a particular variable, and then your memory usage is twice as high.
So I have some like bad ideas around how you can use like C extensions and like create like a custom parser, because like JSON's not a regular language, and like only select the keys that you need. But like, do people actually create such monstrous JSON files in real life in your experience, or?
I have not seen that. I am not I have not seen like a broad variety of JSON in the real world, so I can't tell you what people actually use. The iJSON library has this little query language, and I suspect for like the majority of cases, they are relatively simple. So you can use that, and it will parse things incrementally for you. But I have to assume that someone somewhere has done something that does not work for them.
But it's like, I just kind of feel like you have to have made so many bad decisions on the way. Is the library going to help them? Like,
Yeah. So yeah, there is some point where like the correct answer is you need a better data format.
yeah, right. So
I think this went to the solution that you mentioned about loading just the data that you need. And on your screen, I don't know if I saw this correctly, but it seemed like even this library message spec is loading the entire data. So I was confused whether, how does that relate to loading only the subset of the data?
So the question was, sorry. Yeah, so the question is, isn't this loading the whole thing into memory? And so how is that loading only a subset? So the thing to notice here, there's two, in this case, you're ending up with two copies of the data in memory. One is just the bytes on disk from the JSON, and the other is the Python representation. So the bytes in memory, like on disk or in memory, like they're not a thing you can interact with, right? It's just a pile of bytes. You want some objects. And so here, because the API for message spec requires you to load the whole, it doesn't have an API for loading from a file, which is kind of annoying. You do have to load the whole thing into disk. But the peak memory, so the file is 50 megabytes, the peak memory is 110. 10 of that is a Python interpreter. It's about 2 times the size of the file in memory. And all the previous examples were more than that. They were like 2.8 or 4.6. And so even though you have to load the whole thing into memory to parse it with message spec, by not loading the records you don't care about, parts of the record you don't care about, we still save memory. But yes, this is, if message spec allowed you to read directly from a file, it is quite possible that you get memory down to about 50 megabytes. And you wouldn't have to waste memory on reading all the bytes.
I was going to mention, so like BSON has like a length field where like you'd be able to actually scan it more efficiently, like for each member. So even if you still want to do something JSON-like, it would just be converting it to BSON potentially.
Yeah. So yeah, a JSON is just hard to parse in a memory efficient way because you don't know how long things are. A bit like CSV, not as bad as CSV, but still. And so yes, it's just not a great memory format. But if you do need to, you do have options. Okay, so I will turn to the last slide, and thank you very much. And yeah, feel free to email me or to talk to me afterwards.